Hello, let's talk about isolated systems while dealing with momentum. We did this before in energy, but now we're going to do it with momentum. So you have a system, and then you have particles interacting in between them, like the, I don't know, two cars crashing, two particles feeling electrical repulsion, or two particles feeling gravitational attraction, or two things touching because of the normal. It doesn't matter. You have two or more particles. It's a system of two or more particles and is isolated. So no external forces. But I told you that Newton defined its actual equation not as just ma. That's not what he did. Newton's second law in reality is the change or the first derivative of momentum with respect to time, which in this case, well, is zero because there is no external force. If it's isolated, then this is equal to zero. That means you can do it. That means the momentum is not changing, and so there is delta p is zero of the total momentum. This is the total momentum of the system. I should say here system. That will be the first derivative of mass 1 velocity 1 plus mass 2 velocity 2. Okay, that's because we have two objects. One is moving like this, one is moving like that. This is mass 1, this is mass 2 of v2 and v1. Okay, so then this is zero. So the change is zero. So the total momentum, right? The total momentum, well, this is the total momentum. And it is not changing. So if the momentum is not changing, that means momentum final minus momentum initial is equal to zero. And because in this system we had two particles, for two particles, then we have momentum final for particle 2, or well, particle 1, let's say. Particle momentum final for particle 1 plus momentum final for particle 2 minus the momentum final for particle initial, my goodness, initial for particle 1 plus the momentum initial for particle 2, this must be equal to zero. So another way to write this will be particle momentum 1 initial plus momentum 2 initial is equal to momentum 1 final plus momentum 2 final, right? And then because they're all vectors, then we have to put the little line on top to remember that these are vectors. Because if total momentum is conserved, then the total momentum in x is conserved, the total momentum in y has to be conserved, and the total momentum in z has to be conserved. And what this is going to give us is, well, versions of these equations in each one of the directions. Momentum 1 initial in the x-axis plus momentum 2 initial in the x-axis is equal to momentum 2 final in the x-axis. Let's do it properly. Momentum 1 final in the x-axis plus momentum 2 final in the x-axis. And the same thing here. So I just put all the equations to spare you the pain of watching me write all those symbols in what is now a subscript festival. But that's what the equations look like right now. Now, what the book will tell you is that this conservation of momentum can be written as whenever two or more particles in an isolated system interact, the total momentum of the system does not change. Notice that it doesn't mean that the momentum of one of the particles is not going to change. If the particle interacts with the other, it can transfer momentum from here to the other one, or vice versa. But the momentum of the whole system is not going to change. And these will be very powerful equations, right? Well, it's called conservation of momentum, right? And it's as powerful as conservation of energy, for instance. Conservation of momentum can help us answer a question like this one. This is a question the book asks in section 9.1. You can go back and read it. The first time they ask this, we realize we don't have the means to solve it. If you want to do forces, yes, you could. You could say the force that the archer exerts on the arrow, let's call the archer Joe. So the archer is called Joe. The force that Joe exerts on the arrow is equal to the negative of the force that the arrow exerts on Joe. But that will be not enough to find the velocity of Joe. They're saying the 60-kilogram archer stands at rest on frictionless ice and fires at 0.030 kilogram arrow horizontally at 85 meters per second. And the reason is we don't know anything about the acceleration of the arrow because we don't know anything about the force that with which the bow is accelerating the arrow. If you try to do this through work, similarly, we know nothing about the forces, so we know nothing about the work. So you cannot use energy alone. But if we use momentum, then we already have everything we need. What we can do is treat the system as isolated, and then recognizing there are two particles in the system, which is the arrow and the archer. Okay, so we're not going to do this. Instead, we are going to say that the total momentum in the x-axis doesn't change. And that means momentum of, let's keep calling it Joe, the archer is Joe, okay? So the momentum of Joe, initial in the x-axis, plus the momentum of the arrow initial in the x-axis has to be equal to the momentum of Joe final in the x-axis plus the momentum of the arrow final in the x-axis. So that means mass of Joe, velocity of Joe initial x-axis plus mass of the arrow, velocity of the arrow initial in the x-axis is equal to mass of Joe, velocity of Joe, a final in the x-axis plus mass of the arrow, velocity of the arrow final in the x-axis. I laugh because it's a lot of subscripts. And there you go. They are asking us the velocity of the archer after. So what they want is the velocity of Joe here. This is the number we're looking for. So we have to solve for it. And then the equation is going to look like this. Well, first we're going to simplify. At the beginning, nothing is moving, so these two values are 0. Thank God we don't have to rewrite all those subscripts. So from the equation, we simply isolate the velocity of Joe final in the x-axis to be negative the mass. Well, this term goes on the other side as negative, of course. Mass of the arrow, velocity of the arrow final over mass of Joe. And we simply substitute all the numbers. The mass of the arrow, 0.03 kilograms. The speed of the arrow is 85 meters per second. And then the mass of Joe is 60 kilograms. And what we get is that the speed, or actually the velocity of Joe in the x-axis is negative 0.042 meters per second in the I, and now we put the little line. Like here, I put all those subscripts, but technically you still need to put the V. No, it's not true. If you put the x-axis, you don't need the line. Yeah, it's already clear enough that this is a vector, right? So we can leave it like that. We can just say the velocity final happens in the x-axis, right? So you have two options here. You either put it like the velocity, so plus in the x-axis, you put it like 0.042 meters per second, and it's already understood you're in the x-axis. If you don't put the x, then you have to put the I unit vector, right? There you go. So you see how powerful this new conservation of momentum business is. In the next video, we'll practice more these problems in class, and in the next video, we will talk about the non-isolated version of this.